Okay, so in this video I want to focus on Faraday and Lenz's law. I will choose questions that involves both Faraday's and Lenz's law. So that means for questions that only determines magnitude of induced EMF and induced current, I won't be focusing at all. I will be looking for those that involves direction as well, just to have a practice. Okay, so let's look at this first question. Okay, the figure shows a square wire loop of 2 meter sides connected to a 0.5 ohm resistor placed perpendicularly to a changing magnetic field. So that means my magnetic field is changing, it's not equal to 0, my dB is not equal to 0. If the magnetic field changes uniformly from 0 to 0.4 Tesla in 6 seconds, calculate the magnitude of induced EMF and the induced current in the loop. Also, determine the direction of the induced current. So, I just want to remind you that Faraday's law says that the induced EMF, induced, comes from a few things. You can induce EMF by changing either the magnetic field or changing the area, or you can also change the angle. So if you see any of these three things changes, then you are most likely going to have induced EMF. If you have induced EMF, that EMF is going to drive the electrons to flow, which gives you current. Okay, so here we have area, right? Area of the square, which is just 2 meters by 2 meters, which means this is going to be 4 meters square, right? I have resistance of 0.5 ohm, and also my magnetic field changes from 0 to 0.4. That means my dB over dt is going to be 0.4 minus 0 over 6. Okay, 0.4 over 6, which is just 40 over 60. Sorry, 4 over 60. Which means that I have dB over dt of, let's see, I have 1, I have 1, and then 15. Alright, 1 over 15. So if I were to determine the induced EMF, because this is a single loop, right? This is just a single loop, you don't have multiple turns, then your induced current is induced EMF is just your A times your dB over dt. This is your magnitude of your induced EMF. So then you have 4 times 1 over 15. So 4 over 15 is simply approximately 0. Let's see, let's calculate that. I have 0.267, so approximately 0.267 volts. So that is the answer for the first part, which is determine the magnitude of induced EMF. Now, this induced EMF, right, is going to create an induced current. So what I can say is that induced EMF is equals to I induced times R, and this is, then I can just substitute the values. 0.267 equal to I induced times 0.5, right? Or I can put quite simply 4 over 15 equals to I times 1 over 2, which means that my I is going to be 8 over 15, which is approximately 0.533 amps. So that is the answer for the second part, which is the magnitude of induced current. Okay, and last but not least, I want to look at Lenz's law. I want to know the direction, right? And to do this, I do a simple table where I can see that the original magnetic field, is pointed into the page, right? And because it increases, so 0 to 0.4 is an increase, to increase, you introduce a magnetic field that is same direction. So this is the change, and then Lenz's law will react to that in the opposite direction. That tells me if I were to apply right hand rule, it is out of the page, this is going to be counterclockwise. So this 0.533 is going to be counterclockwise. Okay, so those are the three information that I have figured out from this problem. All right, okay, so let's look at the next problem. Okay, so here we have another question that involves both Faraday's and Lenz's law. This is quite the opposite from the question before, in that this is a case where the diameter change. If the diameter change, then your area changes. Okay, so let's just read the question for now. A 14-turn circular coil, all right, so my N is 14, and it lies in a 1.2 Tesla magnetic field pointing inwards, right? So my magnetic field is 1.2 Tesla. Inwards means moving away from me, so what I'll be seeing is a cross, right, an X like that. The diameter changes from 22.5 centimeters to 7.2, so the diameter changes from 22.5 centimeters to 7.2. If I were to find the radius, I will just divide this by 2. I will have 11.25. Yep, 11.25. 25 centimeters, and then finally I have 3.6 centimeters. Right, so what that means is that my area change, the change in my area is going to be pi r square minus r square, which is 0.036 square minus 0.1125 square. And then if I were to find that as a function of time, divided by time, per unit time, I'm going to have I just going to divide by 1.8. Okay, I'm just going to divide that by 1.8, and this would give me a value of 0.0198. So delta A over delta T is 0.0198 meter square per second, just to remind me. Okay, so now what I need to do is I need to multiply them all, which is I need to multiply B and B and N, and then delta A delta T. So my induced EMF is going to be N times B times delta A over delta T. So my induced EMF is going to be 14 times 1.2 times 0.0198. Okay, so that means my induced EMF, right? Yep. So my induced EMF is 0.33 volts. Okay, so that's the answer for the magnitude of induced EMF. After that, I need to find out the magnitude of induced current. This is just going to be epsilon I equals to II times R. That means my II is equals to epsilon I over R. That means I have to divide 0.33 by 7.5, and this should give me around 44.4 milliamps, and that is my answer for the second part, which is the magnitude of induced current. So Now what I can do is I can apply Lenz's law. Again, my original is into the paper, inwards the paper, so that means it's going to be x. My change, if you look at the area, it actually decreased, right? Area decrease. So that means I have to introduce, that means the magnetic flux is decreasing. I have to introduce an opposite action to the original, and when I apply Lenz's law, I will react to the change. So that means it's going to be in the same direction as the original one. And if I have my thumb pointing into the, let's say, the screen, right, or into the paper, I will have it clockwise. So when I apply right hand rule, I will have clockwise. So that means the induced current 44.4 amps is going to be clockwise. All right, so that is the answer for the third part, right, which is the direction of induced current. Okay, all right, so let's move on to the next question. Okay, so we are on the third question. This is going to be a question from 1920, right? Right off the back, we can see that this question is a question on straight conductor. What that means is that the induced EMF is going to be equal to BLV, where L is in fact the length of this part, which is 0.2. Okay, all right, so this is my L. Okay, so I can right off the back read the question, and it gives me a few information. The first information that's giving me is that the loop is 30 by 20. That's fine, that's indicated in the diagram. And then we also have the value of V, which is 12 meters per second. And I also have magnetic field B of 0.8 Tesla. And then I also have an induced current in the wire, which is 3 amps. So in a straight conductor, I have induced EMF equals to BLV, but it also equals 2II times R, which is just Ohm's law. So I am looking for the resistance of the wire loop and the direction of induced current. So let's do that. If I were to find the resistance, I can quite easily say that my BLV is equals to II times R. My R is equals to BLV over II. Okay, so that means I can quite simply substitute those values. I will have 0.8 times L, which is 0.2, then times V, which is 12. I divide that by my current, which is 3. I will have R equals to 0.8 times 0.2 times 4, which is just 0.8 times 0.8, which gives me a value of 0.64 ohm. So that is the answer to the first part of the question, which is what is the resistance of the wire loop. Okay, and then for the direction of the induced current, I will use my right hand rule, right, reminiscing of the previous chapter, which I can say F equals to QVB. This just gives us the direction of the current. Now if I have V, right, my V is going to be my forefinger, forefinger, and then I have my magnetic field to be my middle finger, then my F is going to be my thumb, right? So if I were to point V to the right, then my magnetic field to be upwards because we have magnetic fields going north to south, right? Okay, therefore my force, the force on the current or positive charges, is going to be downwards, which is Q to P. So it's going to move from Q to P. Alright, if I were to explain, I just use the right hand rule to determine the direction of induced current. Okay, so that is all for the third question. We'll move on to the fourth and last question for this video. Okay, so here's another question, the last of the question for this video, which is again a straight conductor case. So straight conductor, right? That means my epsilon is going to be BLV equals to IR. Okay, so here I have again my B is 0.7, my length is 0.6, and then my V is in fact 5.7 meters per second, meters and Tesla. Okay, and then my R is also given to be 5 ohm. If I were to find the magnitude of induced EMF, I will have to just multiply B, L and V. I will have 0.7 multiplied by 0.6 multiplied by 5.7. So my induced EMF is going to be 2.394 volts. 2.394 volts. Okay, so that's the answer for the first part, which is the magnitude of EMF induced. For the second part, quite simply, I will take epsilon I equals to II times R. I will have 2.394 equal to II times 5. That means my induced current will have a magnitude of 0.479. So 0.479 amps, and that is my answer for the magnitude of current induced. If I were to determine the direction, right, I will have to look at F equals to QVB. Okay, so my V will have the direction of to the right, and I will indicate this using my index finger. And then my B is going to be out of the page, and this is going to be indicated by out of the page. There we go. It is going to be shown by my forefinger, and my F is going to be indicated by my thumb. So wait, V is my index finger, out of the page, my F is downwards, so that tells me that it is the direction of induced current is either downwards, or I can also say clockwise. Okay, all right.